Hello everyone. Am I audible? Okay, so let's start. Welcome you all to this second week of live mentoring session. So, as all of most of the of you are new, joined are joined today only. So, I will briefly discuss about this course. So, in this course, I will mostly solve around a few questions from the previous year GATE question paper, and I will also try to cover the concept which will be associated to those questions, and it will be mostly a live interacting kind of session, so don't hesitate to ask question at any point of time. You can also interrupt in between the solving question solving also, or you can ask after the solution has been done, then also you can unmute yourself or you can type in the chat box also. So don't hesitate to ask any questions, and I hope most of you are around in second year or third year or fourth year in uh, your BTech, right? Even if you are in the second year also, there no problem is there. So I will try to cover the concept also, so that you can understand. And if you have any problem or any doubt at any point of time, you can stop me and ask question. So now let's move into the first questions. This is the question number 42 of GATE 2016. So the question is, zinc oxide is reduced at a constant temperature in a closed reactor using ZNO and carbon in the solid form as the only starting materials. So the following reactions are assumed to be thermodynamic equilibrium, and the reactions are ZNO plus carbon in the solid form is equal to Zn in the gaseous form plus carbon in the gaseous carbon monoxide in the gaseous form. And the second reaction is 2 mole of carbon monoxide is dissociating to give rise is dissociating to form 1 mole of CO2 and 1 mole of carbon. So assume ideal gas behavior based on the mole balance. The relationship applicable to the system at equilibrium is option A is Pzn is equal to Pco plus 2PCO2. Option B is Pzn equal to 2PCO plus PCO2. Option C Pzn equal to PCO plus PCO2. And option D Pzn is equal to 0.5 PCO plus 2 PCO2. So my screen is visible to all you all, right? So now let's solve this question. So what is first given that in a closed reactor, uh, only ZNO and carbon was the only starting material. So let's say this is a closed reactor. So in this at the starting, only ZNO in the solid form and carbon in the solid form was there. So and then these two reactions is happening inside this closed reactor, and because of this reaction, what will be the different compound that will be present in this at the equilibrium. uh, so those are zinc in the gaseous form, carbon monoxide in the gaseous form, carbon dioxide in the gaseous form, carbon in the solid form. So this will be the product phase, right? So, and also the unreacted carbon in the solid form and unreacted Zn in the solid form will also be there. So at the equilibrium. So now, anyone has any idea how to approach this question? Anyone try to answer? You can unmute and answer how to approach. Okay. Uh, Basically we have to do mole balance here, so it is also mentioned in this question itself. So based on the mole balance, we have to find out at the equilibrium what are the number of mole of this gaseous compounds are present, because in this closed reactor only that element or compounds, those will be in the gaseous form, those will exert pressure on the chamber. Solid will not exert any pressure on the chamber. So we have to know the total number of moles of these gaseous elements that are present at the equilibrium. So for this we have to first do the mole balance for for these two reactions. So now let's write the reactions here. Zn in the solid form plus carbon in the solid is equal to Zn in the gaseous form plus CO in the gaseous form. And the second reaction is 2 mole of carbon monoxide in the gaseous form is forming 1 mole of CO2 in the gaseous form plus 1 mole of carbon in the gaseous form. Now, as here 2 mole of carbon monoxide is there, so just to do the mole balance, I will multiply the both side of this equation by 2. So now these two equations, this mole balance is done. Now, so this is the initial condition and this is the equilibrium. Now let's say at initial condition for these reactions we had 2a mole of ZNO and 2a mole of carbon in the solid form was initially there. Let's say 2a mole of ZNO was there initially at the chamber and 2a mole of carbon was there initially at this chamber. So this is a random, you can take anything, like you can take 2a, you can take a also. There is nothing in that. So as I have multiplied by 2, so just for the simplicity I am considering it 2a. So so initially there is no other element was there, so this is also 0, this is also 0. So for this reaction also initially nothing was there, 0 and 0, let's say. So now at the equilibrium, let's say if from this 2a mole of ZNO, 2x mole of ZNO is dissociating, then also this that this carbon will also dissociate with this ratio, that is 1 is to 1. So if 2x mole of ZNO is dissociating, so also 2x mole of carbon will dissociate. So how many mole of zinc and carbon monoxide will form? It will be also so as 2x mole is dissociating, so 2x mole of zinc will form here and 2x mole of CO in the gaseous form will form here. Now this 2x mole of CO which is formed because of this first reaction will act as a reactant of this second reaction. So initially for this reaction we can consider 2x mole of carbon monoxide is there. So now let's say from this reaction at equilibrium, 2y mole of carbon monoxide is dissociating. So if 2y mole of carbon monoxide is dissociating, how many mole of carbon dioxide will form? It will y mole of carbon dioxide will form, because you and also y mole of carbon in the solid form will form, because you can see that this is 2 1, here it is 1. So basically the ratio is 2 is to 1. So if 2y mole is dissociating, so y mole of CO2 will form. Now we have the number of mole that are present in the equilibrium. So for this reaction, this is the number of mole and this is the number of moles. So now we can write how much mole of Zn is present. Zn, as you can see, this is the Zn. So 2x mole of Zn is present at equilibrium. How much mole of carbon monoxide? Carbon monoxide first forming here and then again it is dissociating. So we have to take this mole number as a total number of mole that is present in the equilibrium. So carbon monoxide it is present 2x minus 2y mole, right? And the carbon dioxide, how many mole of carbon dioxide is present? It is y mole of carbon dioxide is present. Now this carbon and unreacted carbon and ZNO are in the solid form, so they will not exert any pressure to the this closed reactant. So only these three will contribute to the pressure. So now it is also mentioned that the reactor is at constant temperature and it is a closed reactor. So constant temperature means T is constant, and closed means V is also constant, right? So now in the question it is mentioned that assume the ideal gas behavior. So if you assume the ideal gas behavior, PV is equal to nRT, right? So here T is constant and also V is constant. So you can write that P is equal to N into RT by V. That means P is proportional to the number of moles of that elements present in this closed reactor at the equilibrium. So you can write that P of Zn is equal to number of moles is 2x. So 2x into RT by V. Similarly, you can write P of CO is equal to 2x minus 2y RT by V, and P of CO2 y into RT by V. Now this is equation 1, this is 2, and this is equation 3. Now you can see that if I take this equation, that is equation 2, so we can write that PCO is equal to 2x into RT by V minus 2y into RT by V, right? So what is this 2x minus 2x into RT by V? It is nothing but PZN, right? So 2x into RT by V is nothing but PZN minus 2 into y into RT by V. What is y into RT by V? Y into RT by V is nothing but P of CO2. So P0 is equal to PZN minus 2PCO2. Now we can write that PZN is equal to P0 plus 2PCO2, right? So this is the final answer. So option A is the final answer. So anyone has any doubt in this question? All of you have understood? Okay, so everyone is okay with it? Should I move to the next question? Okay, okay, now let's move into the next question. Okay, so this is the next question. Uh, so this is the question number 43 of GATE 2016 Metallurgical Engineering. So this question is on the undercooling of a liquid to form a solid. So the question is the critical nuclear size when copper melt is undercooled by 100 Kelvin. These are the given data that melting point of this copper density, solid and liquid interfacial energy, latent heat of freezing, and molar volume. This data are given. We need to calculate the size of the critical nucleus. Uh, so there is a unit error is there. It will be meter cube mole inverse. It will not be meter to the power minus 3 and mole. So so we have to calculate the critical nucleus size. So anyone here want to answer what is the critical nucleus size? What is it? You can type in the chat box also, or you can unmute. What is a critical nucleus size? Okay, okay. So how to solve this question? How to approach it? So what is the formula? You know? Okay, okay, you are right. Okay, so so critical nucleus, yes, you mentioned it correctly that when we undercool the liquid, so what happens? Liquid basically that random arrangement of atoms are there, right? But solid is a in solid the regular arrangement is there. So in liquid, when it is in the liquid form, it happens like that. Randomly, few of the portion of this liquid suddenly come into the regular arrangement, and again it will become random arrangement. So this kind of process always happens in the liquid. So small range cluster forms in the liquid, and it also breaks simultaneously. So it is not stable at above the melting temperature. When T is greater than Tm, this small cluster will not be stable above other melting temperatures. But this kind of phenomena happens simultaneously all the time. Now, if you decrease the temperature below Tm, so if you decrease the temperature below Tm, what will happen that uh, this, let's say this one cluster is there, which is regularly arranged. So it is by the Shorter's ordering, it is formed. Now, uh, when one more atoms jumps into it, so it becomes stable. Like that stability is given by the Fibonacci and diagram that I will show you later. So this smallest size of this cluster, which is stable, is basically known as the critical nucleus size. So now, what is why the if you go below the Tm, why that liquid is forming solid? Because if you draw the free energy versus temperature diagram, you will see that this is the G versus T. So T is increasing along this axis. So this is the T melting. This is the T liquid and G liquid and G solid. Above the melting point, the free energy of the liquid is lower, and below the melting point, the free energy of solid is lower. So now, uh, here it is mentioned that we have undercooled by 100 Kelvin. So that if it is Tm, this point is Tm, melting temperature, where the free energy of solid is equal to free energy of liquid. Now you have undercooled it below 100 degree. Means, so that difference is delta T is 100 Kelvin. Okay. So now this difference between these two line, if I draw with a different color, that will be better. Yeah. Let's say this red line is for the liquid, and this line is for the solid. So this difference between these two at this temperature, that is delta G. So this is the driving force for the solidification. Now, how this formula is coming? Anyone? How this equation is coming? Every one of you might have remembered these equations, but how this is coming? This R star is equal to 2 comma by delta GV. Anyone try to answer? Okay. Uh, so this is the driving force, as I mentioned that delta G is the driving force for the solidification. So it is it will this driving force will assist the solidification process. But when solidification occurs, initially everything was liquid, right? So now, once one solid is forming, if here one solid is forming, so a new interface is forming here. That is solid liquid interface is forming, right? So, so because one new interface is forming here, see it also requires some amount of energy. So this formation of this new interface is basically opposed the solidification kind of thing. So energy will be required. So we have to provide the sufficient amount of energy to form this surface. So we have two opposing effect for solidification. So if we write delta G is the free energy change for solidification. Now it has two opposing thing. One will assist. What will assist the delta GV, that is the driving force. So this is the energy per unit volume. So this will be multiplied by 4 third pi r cube. Let's say one spherical solid is nucleus is formed whose radius is r. So this will be 4 third of pi r cube plus that because of this new interface is creating, so it will also associated with some energy, that is gamma s, and it is a surface free energy, so we have to multiply it by uh, its surface area of the nucleus. So now uh, this is one term, it is assisting and it is opposing. So if we plot the delta G with R, so we'll get that this is proportional to R square and this is proportional to R cube. This term is proportional to R cube. This is negative because free energy is decreasing, right? So this is negative. So this will be in the negative side and this is positive. So it will go upwards. So now if you take the resultant, so resultant will be like this. Now you can see that there is a highest critical point is there. So this is the R star. Like if R star, this size of nucleus is formed. Now it is kind of at a metastable state, right? Now if one more atom is jumping into this cluster, its radius will further increase. So if this radius increase, its free energy is also increasing, decreasing, right? So it will be stable again. So this, that's why it is called the critical radius. So how you will get the equation? If we take the derivative at this point, we will get that delta G, T of delta G by dr will be 0 at this point, at the maximum point. So you can write that 0 is equal to delta GV into 4 pi r square plus gamma s into 4 pi into 2r, right? So this will be r star now because we are considering at this critical point. So now from here we'll get that r star is equal to minus 2 gamma s divided by delta gv. So this is the equation that using this we can calculate the critical radius, right? So now few of the value we have are given, that gamma s is given, also Tm is given, latent heat is given, molar volume Vm is given, and density rho is given. But from this formula we only know that gamma s only, right? So we need to calculate the delta gv. How you will calculate the delta gv? So as I mentioned here that this is the, sorry, this is the liquid, this is the solid, right? So this is the Tm and this is our T, temperature of interest. So delta G is, we can write the delta H minus T delta S, right? So at melting temperature it will be delta G m is equal to delta H m minus T m delta S m. So at melting temperature this delta G is 0. So we'll get delta S m is equal to delta H m by T m. Delta H m is nothing but the latent heat by T m. Now we can put this delta S value here in this equation. So we'll get this delta G, this difference. We are putting the same delta S because it is almost straight line. That's why that slope is equal at every temperature. That slope is equal. Also, that intercept will also be equal. That is delta Hm, delta H and delta S are equal. So delta G is equal to Delta G is equal to delta H m minus T into delta S means L by Tm, right? So now we can write delta G is equal to delta H m. It is also L or delta H m. You can write this is same. L delta H m is the latent heat. So delta H m into 1 minus T by Tm. It is delta H m into delta T by Tm. Now, the delta Hm value is also given, that is the latent heat is given. How much is the value? 13,000 joule per mole. So now we can calculate 13,000 joule per mole. Now this will be negative, right? Because while freezing, that latent heat is releasing. So that will be negative into delta T. What is the delta T? That is the undercooling. This undercooling, that is 100 Kelvin. It is given. It is so 100 Kelvin. Now divide by Tm, melting temperature. Melting temperature is 1356 Kelvin. Now if you calculate this one, can anyone calculate and let me know the answer? What is how much it is coming? Anyone? All of you have calculator with you right now? Yes. Yes. 958.7 joule per mole. Right? The Kelvin will cancel out. So now in yes, negative. Sorry. Okay, I'm writing below 985.7 joule per mole. Now you can see that this is delta GV and this is delta G. These two are not totally equal because delta GV is the free energy change per volume, is unit volume. So, but it is the per mole only. So it is not per volume. So in order to get delta GV, we have to divide the delta G by molar volume. So how much will be the 985.7 divided by what is the molar volume is given 7 into 10 to the power minus 6 meter per mole. So this is joule per mole and it is 7 into 10 to the power minus 6 meter cube per mole. So how much it will be? Minus, oh sorry, thank you for correcting, 958.7. 958.7 divided by 7 into 10 to the power minus 6. So how much it is coming? Minus 136.957, right? Into 10 to the power 6 joule per meter cube. Can anyone check if it is correct or not? Okay. Okay, now we have all these values, that delta GV we have calculated, and this gamma also, gamma S, it is given 0.5 joule per meter square. So now we can calculate that critical radius. What is the critical radius? Then it is minus 2 into gamma S. Gamma S means 0.5 joule per meter square. It is given, and this the delta GV is this minus 136.957 into 10 to the power 6. So how much it is coming? That minus and minus will get cancelled out. So now how much the critical radius is coming? Anyone? Anyone has calculated it? Okay. 2 into 0.5 divided by 136.957. Yes. So it is coming 7.3 into 10 to the power minus 9 meter. So if you write in terms of millimeter, then it will be 7.3. It is in meter, so it will be 7.3 nanometer. Right. So the correct answer is option D. So anyone has any doubt here? Because as I have explained lot of things like how these things are forming and all. So everyone understood that how these equations are coming and how the solidification process is actually occurring and what is the concept of critical nuclear size. Okay. Yes. 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 Basically, there is a assumption that this free energy line I have drawn, right? Okay. Let's draw again with the trace. Yes, like for a very means small range of temperature, like 100, 200 or 300 kind of, in this it is assumed that these free energy lines are almost straight line. In reality, it might be a curved line, not it is not necessarily it will be always straight line, but there is an assumption that these are the straight line. So assuming these things, actually we can then put that delta Sm here because that change if it might be there is a change in the slope, that is the delta s might change, but that change is very negligible. Delta h and delta s, that change is sometimes it becomes very negligible. That's why these lines are considered almost as a straight line. So the slope will be same at any point. If it is curved line, then the slope will get changed. So as the change is very much negligible, so it is assumed that they are almost straight line. So assuming that we get that slope is delta s m, so this will be same at every point. Like if it is here the slope is delta s m, so at every point it will be same because it is a straight line, right? And also the intercept is delta h m, right? Because if you make the t 0, you will get that delta g is equal to, this is delta g axis and this is t. So t is 0 means delta g is equal to delta h at t is 0. That means the intercept is delta h. Okay, so as it is straight line, so this intercept will also be same. So that's why it is assumed like there is a very minute change in the enthalpy. That's why it is assumed that it is almost same. So that's why we have actually uh, put this value in this equation. So this is the reason actually. Yes, means if you are going with very means less temperature, then that change might be a like means that time that change may not be a negligible change, but mostly that delta H part, that change is very much negligible as compared to delta S. Sometimes delta S may get changed. So that sudden change in delta S is happening at that melting point only, because suddenly it is coming from the uh, liquid phase to a solid phase. The sudden change is there, but after that in the solid phase, that delta S change is not that much. Means with decreasing temperature, that entropy change mostly is very much random or vital. You can say in the gaseous form or somewhere there. With temperature, entropy is a strong function there. But in case of in case of solid state, So these are a negligible change in these two things are there, that's why. So if even if you are assuming, so it will not leads to a very means vital error or this kind of thing. Anyone has any other doubt? Everyone is okay with it? Okay. So now I have one question like like once we do the solidification like from the liquid to from the liquid. Okay, let's go to the new page. When we are going from liquid to solid, we need a certain amount of undercooling, right? So at if we keep the liquid at exactly at tm, it will not solidify, right? Because as we saw that there is a two opposing effect is there. One is for the volume. This is the driving force, and uh, this is the energy required for creating a new surface. Now, if you are at this point, so here delta G is 0, right? So you are not getting any driving force there. It is totally 0. So you are not getting a sufficient energy to create this surface. So solidification will not occur exactly at Tm, right? So you have to give certain amount of undercooling, like you have to go to below Tm. So then only it will start to form the solid nucleus of solid. So and that undercooling, how much it is required, it will depend on whether homogeneous nucleation is happening or heterogeneous. For heterogeneous nucleation, that inclusion or again means other different phases provide a surface for the nucleation. And so for this heterogeneous nucleation, that the undercooling required is less, but for homogeneous nucleation, that undercool sometimes it requires more than 200 or like this. So now my question is, if you go from solid to liquid, so in that time also do you need superheating? Like here you are it requires undercooling. Why? It is needed superheating or not? It is needed. Why? Means why you think it superheat is needed? So that how it will be decided, right? So like now you took this solid block in a atmosphere or in this spot. One solid block is there, right? So now which interface it is having? Solid with vapor, right? So that interface energy is given by gamma SV, right? Now you are heating it, let's say at melting point. Now for the time being, let's say it is forming liquid and it started forming liquid. So this is solid and there is also liquid layer is formed, right? So what will happen? So for liquid layer, it will create liquid vapor interface. So that interface will have energy gamma liquid LV, and this another interface. This is the solid liquid interface. So this interface will also have some energy that is called gamma liquid solid, right? So basically you are breaking this interface, gamma solid vapor interface you are breaking, and you are creating two new interface, gamma liquid vapor and gamma liquid solid. But what happens is that gamma solid vapor in this energy is greater than gamma liquid vapor plus gamma uh, liquid solid. So that means when it is melting, So that energy is basically decreasing. So so it is favorable. It is not requires any extra energy to form this kind of surface, because already that energy it is having associated with this surface, it is only contributing to this forming these two surface, and also this energy is quite higher than the total of these two energy. So that's why when we heat a solid and during melting, so we don't need any superheating. Or at the melting temperature itself, that solid will start to form a liquid. So you don't need any superheating kind of thing in this case. But in case of liquid solid, that liquid vapor interface is breaking, and you are forming solid vapor plus liquid solid. So in that case, what is happening? This energy is less. So when you are going from this direction, this to this direction, you are going towards the higher energy uh, things. Means it will increase the energy of these interfaces. So that is not favorable. So for this, you need to give certain amount of driving force. So that driving force is given by this decreasing the temperature. As you decrease the temperature more below the Tm, as you can see, the driving force is increasing, right? Here this distance is this. Here this distance is much more. So from liquid to solid, if you go, you have to give much more means you need undercooling to give some driving force so that uh, it can means it can get that certain amount of energy to form these two interface. But in this case, this is not required. So that's why we don't need superheating while during melting. Everyone got it? Any doubt? So should I move to the next question then? Yes. That that actually basically calculated experimentally or kind of thing like. So just means from just seeing these things, you won't you you don't know that that energy will be higher or something like this. But experimentally it is found that this energy is this surface energy between these two is higher than this liquid vapor and solid liquid. So that's why every time when you melt, you will find that at the melting temperature itself it is melting. So if you like put one gold sample inside the furnace at the exact melting temperature, that is 1064. If you keep this gold sample in a furnace at this exact same temperature, after some times you will see that your gold sample is melted, like it will form, it will melt. But same thing, if you put a liquid gold sample inside a furnace at 1064, it will be at the melted condition only. It will not form solid. So you have to go below 1064, then only it will start solidifying. So these surface energy are basically calculated experimentally, and these are the from the experimental evidence people found it. Anyone has any other doubt or any other question? Should I move to the next question then? Okay. Okay. So this is the one marks question. This is also from GATE 2016. This is the question number 11. So this question is that chemical formula of Wustite is option A Fe2, option B Fe2, O3, option C Fe3O4, and option D Fe1 minus XO. So option D. Why option D? This is a straightforward question, by the way. Yes, but why it is not written as FeO? Why it is written as Fe1 minus XO? What is the reason? Because means mostly we say Wustite is FeO, right? But why it is Fe1 minus XO? Yes, X is what? Whatever saying X is 1. Yes, but actual chemical formula of Wustite is Fe1 minus XO. So you people have get the right answer. But my question is why it is Fe1 minus XO? Why it is not FeO? What is the reason? Why it is not FeO? Like for other, it is mentioned that Fe3O4, Fe2O3, FeS2. But for FeO, why it is not FeO? Means Wustite, why it is not FeO? Why it is Fe1 minus XO? Where X is kind of variable. It is like it may be 0.95, or it may means that 1 minus X. It may be 0.95 or 0.94 or even zero point 0.9 also. So this is a kind of varying things is there. Why this is the case for this Wustite? Why it is Fe1 minus XO? Anyone try to approach? It is not that you have to give correct answer, but it is important that how you are thinking. Why it is happening? Even if you are wrong, you can answer, no problem. At least try. Anyone? It can be. No, not exactly because of the human made you were saying. Some other thing like is associated with it. Uh, okay, let me give some hints like Fe1 minus X O. What it means? It means iron is less as predicted by the stoichiometry. Stoichiometry ratio is 1 is to 1, right? For FeO. This is the stoichiometric ratio. But Fe1 minus XO means this ratio may be 0.95 is to 1 or 0.94 is to 1. So that means in this oxide, the iron present is less as it is predicted by stoichiometry. It is less than that amount. So why this means why it is less? Okay, have you means all of you read crystallography, right? So in crystallography also we have had some kinds of defects, right? What are the different kind of defects in metal you found? Anyone? Mechanical metallurgy people have read, right? In crystal also there is regular distribution of atom is there, right? Yes, vacancy is one type. Yes, exactly. So in case of metal, you will find that maybe some atom is missing from here. So this is a, let's say this is a vacancy then. This is a vacancy is one kind of point defect. Similarly, it may be that this atom moves to these positions. So it is like interstitial defect. Again, if you put another atom, that is an impurity atom. So interstitial impurity defects it may also be present. Similarly, there might be a uh, other substitutional atom is present. So these all are the different type of point defects. That is a vacancy, interstitial, and impurity. So these are for the mostly for the sorry these are for the metal matrix kind of things, right? So this impurity can be either interstitial or substitutional. So similar thing happens in case of this oxide also. So as that metal is not a totally perfect arrangement is there, we always mention that metal is a regular arrangement of atoms and right, but somewhere it may be some vacancy is present, somewhere that impurity atoms may present. So similar situation happens in case of this FeO oxide. So let's say we have this, sorry, better not to put this box. Okay, so let's say this is a Fe. Okay, what is the valency of iron in FeO? What is the valency of iron in FeO? Plus 2. Okay, so I'm not writing in terms of plus iron or something. I'm writing in terms of valency, right? So this is iron. And again, let's say this is oxygen. Minus 2 means oxygen, right? So again, iron, oxygen. So let's say this is oxygen, this is iron, this is oxygen, this is iron, oxygen. Uh, okay, so let's write in terms of valence only. Okay, so if this iron oxide FeO is stoichiometric, this will be the kind of distribution it will have. That you can see that same number of iron and same number of oxygen is there, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So total 10 is to 10 ratio it is present, right? So that means FeO it is. If it is exactly perfectly stoichiometric, then these things happens. But in as in metal also the vacancy is present or some defect is present. Here also some defect is present. Those defects are called there is a two types of ionic defects. One is the stoichiometric and another is the non-stoichiometric. So for other oxide, what happens like those defects for other oxide also defects are present, but those are the stoichiometric defect, right? If you remove this one iron atom and one oxygen atom, you can see that the charge is also balanced because you have removed one plus 2 and one minus 2. So charge is also neutral, and also you can see that you have removed both the atom. So the stoichiometry is also it is also maintained. So now it become 9 is to 9, right? So these things happens for the others three, but for this it is a non-stoichiometric kind of non-stoichiometric defect is found. So non-stoichiometric defect means what happens? Like let's say you have removed one, uh, you have less number of iron is there, right? That means you have to remove one iron. So you have let's say you have removed one iron. So now if you have removed one iron, you have plus 2 charge missing from your this system, right? So now this is not this is no more charge neutral. So you have extra plus 2 minus 2 charges there, extra 2 negative charges there, right? So extra negative charge is there. So how to compensate this extra 2 negative charge? How to make it zero? You have to remove electron, right? You have to remove electron. So now you know that iron has two different type of valency. One is plus 2 and another is plus 3, right? So now what it will do, it will remove one electron from this iron. So it will make, it was plus 2. If one electron is removed, what it will be? It will be plus 3, right? Similarly, let's say it is removing one more electron from this to maintain the charge neutrality. It has to remove two electrons because because of the defect, one iron atom was not there. So there is one iron vacancy is there. This is vacancy of iron cation, right? So to maintain the charge neutrality, you have to remove this two electron. One is removed from here, one is removed from here. So what it becomes now? It is Fe3 plus. It is not Fe2 now. It is become Fe3 plus. That valence is changed. So now that crystal is the oxide is neutral, right? And it has a vacancy of cation. So that means now if you count the total number of oxygen and the total number of iron, you will find that the total number of oxygen here is 10 because we didn't remove any oxygen from here. But total number of iron now become 9. So now this ratio become 0.9 is to 1. So this is just to show the schematic of it, like how this is becoming iron deficient, right? So this kind of defect, when this kind of defect is present, this is known as non-stoichiometric, non-stoichio, non-stoichiometric defects. So this type of defects either it can be uh, means cation deficient or it can be anion deficient. In case of iron oxide, it is cation deficient. That means iron is less, and in some other oxide is there. I think Al2O3 or okay, I'm not sure. So without checking, I don't want to tell. Some other oxide is there where that is iron oxygen deficient. So there it is like let's say AO1 minus X kind of. So there it is oxygen deficient, and here it is iron deficient. That's why that chemical formula of Wustite is Fe1 minus XO. So now you know the answer, right? Why it is happening? It is because of its defect structure. Everyone understood? Okay. Okay. So anyone has any doubt till now? We have solved three questions today, right? So anyone has any doubt on from any of these questions? Everyone is clear? Okay. Okay. No doubt, right? So all the concepts are also clear, like why? Yes. Yes, Devendra. Previous from when you have joined, like this question you missed or the first two question you missed. Okay, okay. So so these questions we basically it was given these two reactions, and it is mentioned that uh, there is a ZNO and carbon was a starting material, right? So this ZNO and carbon was a starting material, and after these two reaction, as a reactant, as a product, this phases are these elements are forming. That is ZN, carbon monoxide gas, CO2 gas are forming. Now also some amount of carbon and ZNO will be as a unreacted part will be there. Now the first step of to approach this question will be like we have to do the mole balance. Even in the question it is also mentioned you have to do the mole balance. So you just simply write these two equation, uh, these two equations, and simply do the mole balance. So as 2 is there, so you have to multiply both the side with 2, and then let's say initially 2 mole of ZNO and 2 mole of carbon was there. So you can take this anything, like it is not necessary you will take 2A, or you can take A also, right? So now if you assume that at the equilibrium from this 2A mole of ZNO, 2x mole of ZnO is dissociating, so it will react with the 2x mole of carbon, and it will form 2x mole of Zn and 2x mole of CO, right? Because you can see that the ratio is 1 is to 1 is to 1. Means although the similar kind of ratio is there. So if 2x mole is dissociating, 2x mole will form. Now this 2x mole of CO, this is forming because of the first reaction. It will be the reactant for this second reaction. So for this, initially we will have 2x mole of CO, and later what will happen? Let's say assume that from this 2x mole, 2y mole of carbon monoxide dissociate. Now you can see that this ratio is 2 is to 1. So if 2y mole is dissociating, so y mole will form, right? Now from the question you can see that this is constant temperature it is mentioned and closed volume it is mentioned. So that means temperature is constant and volume is constant. Now assuming the ideal gas behavior, P is basically proportional to n, right? P is proportional to n. That means that total pressure will be given by the partial pressure, that is total number of mole. So you can write that Pzn is equal to number of moles of Zn, that is 2x. Number of mole of Zn is 2x here, right? So 2x into RT by V. So this is P for Zn. Similarly, you can write P of CO, that is 2x minus 2y, because CO is forming here, like first it is forming here, then it is again dissociating. So the equilibrium amount of CO will be present, that will be this 2x minus 2y. So this is 2x minus 2y into RT by V. Similarly, P CO2 is y into RT by V. Now, if you take this equation, that is PCO, and if you split up this, you will find that 2x into RT by V, that is nothing but PZN. 2x into RT by V is PZN, and this is 2 into PCO2. So you can rearrange it, and you will find that PZN is equal to PCO plus 2 PCO2. So the correct answer for this question is option A. So you understood it, Devendra? Okay, so the next question is also simple. This is a it is asked that you have to find out the critical nucleus size when copper is undercooled at 100 Kelvin, right? So do you know how this formula is coming? That R star is minus 2 gamma by delta GP for critical nucleus, or should I explain? You have the idea about critical nucleus? What is critical nucleus? Okay, critical nucleus is basically that the smallest size of the cluster that is stable when you are solidifying. So, okay, that will be better to explain it from the initially on. Okay, I am writing here. Huh. So, like you have liquid in this chamber, right? So, in liquid, atoms are randomly moving here and there, kind of thing. In liquid, that atomic arrangement is not regular, right? So now, but when you are solidifying, this thing is becoming regular, right? So how it is exactly forming that regular kind of arrangement, how it is coming? So in liquid itself, it is not totally random, you can say. In liquid, what happens, like this one atom, two atoms, some in the small region, it is arranged in a regular pattern. So within the short range ordering, by the short range ordering, but those regular pattern is not stable when you are at Tm or you are at temperature greater than Tm. So what will happen? Suddenly this kind of regular arrangement will form, and suddenly they will break apart. So what will happen? That regular cluster is forming and it is breaking again. So those kind of cluster are not stable at melting temperature, at higher than the melting temperature. Now if you are coming below the melting temperature, that is T and Tm. Now what will happen if, let's assume somewhere that one small cluster is formed. Okay. Now if one more atom joins into it, what will happen? If you are above Tm, this cluster will break down. But if you are below Tm, it will further stabilize this cluster. And so this smallest representative is called basically the critical nucleus. And even you can find out this from this delta G versus R diagram that I will show. So to form a critical nucleus, or for solidification, you have total these two free energy curve. One is for the liquid and one is for the solid. So this cross section is at the melting temperature, where the difference in free energy is zero. That is, G of solid is equal to the G of liquid. But we are doing the solidification at lower temperature, that is at T, that is below 100 Kelvin. So this gap is 100 Kelvin. So now this delta G, that is the driving force for the solidification. But when you are forming a solid, what is happening? One interface is also forming, right? New interface. Earlier it was totally liquid, but when you are forming solid, it is liquid here, but it is solid here. It is solid here. So this interface is forming, right? So to form a new interface, you will need some kind of energy, right? So that's why when you don't have any driving force, so at this temperature you cannot form the solid. So you have to decrease the temperature a bit, so that you have sufficient driving force or sufficient energy to form this nucleus. So for this we can write that delta G for nucleation is delta G into delta GV into 4/3 of pi r cube. Here r is the radius of that nucleus, plus gamma s, that is a surface energy between this solid and the liquid. Gamma s, that the surface energy, so it will be multiplied by the surface area term. So now you have two term here. One is that volume free energy and another is the surface energy. So volume free energy is your driving force, so it is assisting for nucleation. But this energy that is required for creating a new surface, this is opposing you, right? So now if you plot this delta G as a function of r, you will find that one term is proportional to r square. That is positive term, because it is that much energy you have to give. So this term is proportional to r square, and this term is proportional to r cube, right? Because this is negative term, because this is assisting you, because this is the liquid and this is solid, right? So you are coming from liquid to solid, so delta G is decreasing, that means it is negative. Okay, so what will be the resultant will be like this. So this is a critical point or highest point, you can say, of this delta Gn, that is the free energy for nucleation. So now let's say here one, this is r1, this is r star, right? So now let's say this is a small cluster of radius r1, and this is a one cluster that is formed of radius r star. Now what I am doing, I am adding one more atom here, right? And also I am adding one more atom here. So what will happen? This r1 radius will increase a bit. Let's say it is moved into r2, that means it is moved here. Let's say it moved here, and similarly each radius also increase a bit. So it will move from r star to r star prime or r star 1, let's say. So it will move here. So now can you all see that what is happening for these two cases? For the first case, what is happening? R1, as we are adding one more atom, its radius is R2. So it is going to this point. That means its energy is increasing or decreasing? Anyone? Yes, so it is energy is increasing. So will it be stable? Increasing energy is not favorable, right? So that nucleus will not be stable. So this nucleus is not stable. But for this R star, here it is R star. Now, if you adding one more atom, its radius increase and it is here. So now what is happening? Here the radius is increasing, but your free energy is also decreasing. It is not increasing. After R star, means after this point, as you move or as you increase R, your free energy of nucleation is decreasing, right? So that means it is favorable. So this is stable. So any cluster having the radius below R star is not stable, because adding one more atom will unstabilize it. So, but if that cluster reaches the radius of R star, if you add one more atom, what will happen? It will stabilize. So that's why this critical point is called the critical nuclear size. So you got my point, Devendra? Okay, right. So that's why critical, this is the maximum point, right? In this curve. So now if you are differentiate this delta Gn with delta means delta d of delta G by delta dr, so at maximum point it will be 0, right? So now if you differentiate, you will find that this will be delta Gv into 4 pi r square. So it will be r star square, because at this point we are representing r as r star, and now, and this will be gamma s into 4 pi into 2r. So now from this equation you can calculate that r star is equal to minus 2 gamma s by delta Gv. So this is basically now you got this formula, right? How this formula is coming. So now you have to calculate R star. So gamma s is given, but delta GV is not given. So you have to find out the delta GV. So what is delta GV? Delta G I have already mentioned that this distance is delta G. So, and this equation is delta G is delta H minus T delta S, right? So now it is assumed that, yes, so it is assumed that this delta H or this delta G lines are basically straight lines. So the slope is same at every point. So that's why at this point delta G is 0. So at this point delta Hm minus Tm into delta Sm is 0. So you can write delta Sm as delta Hm by Tm, right? So now let's move into this point, that is at which temperature we are doing the solidification, that is delta G. So we can write delta G as delta H minus T delta S. Now as it is assumed that this lines are straight line, that free energy curve, and also there is not very much change in delta H. So that's why you can write here delta H as delta Hm, and you can substitute this T into delta S as this delta Sm, because slope is same everywhere, right? So if you substitute, you will find this equation. So this equation coming from this after substituting this. So delta G is equal to delta Hm minus T delta Hm by Tm. So that is delta G is equal to this one, delta Hm into delta T by Tm, right? So now delta Hm is given. Delta Hm is given. Latent heat of freezing is given 13,000. But it is negative, right? Because you are solidifying. So it is releasing heat. So that is negative. This is minus 13,000 you have to put into delta T. That is the undercooling. That is 100 Kelvin. So that is into 100 divided by Tm. Tm is 1356. Right. So if you calculate this one, you will get that it is minus 958.7 joule per mole. Now this delta G is volume. This delta is not volume free energy. This is free energy per unit mole, unit number of mole. Yes. So now you have to find the delta GV term. In order to calculate R star, you have to find out delta GV. Delta GV is volume free energy. Volume free energy is unit is joule per meter cube. So now you can see that molar volume is given. So what you have to do, that delta G we have calculated 958.7. So we will find delta GV as delta GV is equal to delta G by Vm. You have to divide it by molar volume. So if you divide by molar volume, you will get that the delta GV is minus 136.95 into 10 to the power 6 joule per mole. Even if you don't know, means this you have to divide it in or So you can just simply follow the units, right? So initially it was joule per mole. So now you have to do the joule per meter cube, right? Because it is the volume free energy, so joule per meter cube. So you have to divide it by the molar volume. So now you got that delta GV also. Now it is easy to find that R star, right? Because you know the formula and you already derived this formula, how it is coming. So R star is minus 2 gamma s into 2 gamma s divided by delta GV. So this minus and minus will term will cancel out because delta GV is minus in the negative term. So now we will find that that R star is coming 7.3 into 10 to the power 9 minus 9 meter. So that correct answer will be 7.3 nanometer. So you understood it? Okay. So anyone else has any doubt? Everyone is okay? Okay. Okay, then we'll meet in the next Friday. So and I request all of you to present or to attend this session in every Friday from 6 to 7 and make this program successful. And I will also request that you people can tell your friends also regarding this session so that they can also be means they also can get help from this. And if you people have any kind of feedback that how this session can be so that it will help you people more, you can give us the feedback also, so that we can approach with the NPTEL team accordingly, and we will decide how to proceed this session so that it will be more helpful for you guys. Yes. Okay. This course means that yeah, just 1 week before, means just one class was happened in 12 August. So you have missed only one class, so don't worry. So mostly what we'll do, we'll solve the previous year questions only, but it is not like we'll solve that question only in a simplified way and then it is over. So we will try to cover all the concept that is associated with these questions, right? So that you can understand that how to approach this question, because some questions are there, some people you people can apply the formula and directly get the answer, like in these questions only. If you know the formula, you can apply this formula and you can directly get the answer. So that you can do anytime, even you can do by yourself also. But that idea of this session is that if you have any doubt, if you have any uh, means doubt regarding the concept of these questions, that also I will try to cover, so that you will get to know that means how this thing is coming. Even if you forgot the formula, you will be able to derive that formula. So in this way I will try to explain the question. So I think it will be helpful for you peoples also, like if you know the concept, that will be much more helpful than mugging up the equations and formula, right? So I will also request all of you to ask questions as much as possible, so that that your concept will also get cleared. So and it will be like a more a kind of interactive session. It will not be like any means you come and know the answer of the questions and you go, like it should not be like this, right? So please don't hesitate to ask any questions. Yeah, tell. Yes, 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 yes. Means at exactly at TM solidification will not start, because I have already told, right. As TM, what is happening? This, if you see that this two free energy curve, this two line. So at TM this difference is zero, because at TM GS is equal to GL. That free energy of solid and free energy of liquid is equal. So if you don't need any extra energy, then only at this temperature that solidification will occur. But when when a liquid is solidifying, what is happening first? A cluster is forming, right? So that cluster is getting stabilized, so it will form a small nucleus of a solid, right? So as soon as that nucleus is forming, that means it is creating a new interface with the liquid and the solid. So initially totally everything was liquid, right? So now you are getting extra interface, that is the liquid solid interface. So in order to create that interface, you have to give some amount of energy, right? So now you can see that if you are in this point where the gs is equal to gl, you don't have that available energy that you can give to form a free interface or new interface. So you have to move below the tm, so that you will have a difference between this delta g. So that is that gl minus gs, or gs minus gl, because product minus reactant kind of thing. So that will be negative. Negative means you are getting some energy from this. So that energy will help to create a new surface, right? So that's why you always have to go below the tm to start that nucleation thing, or to get the solidification. And that delta t is also depend on what type of nucleation is occurring. Either it is homogeneous or it is heterogeneous. For heterogeneous nucleation, you have uh, extra surface, like from the inclusion you can get one surface, from the mold wall you will get surface. So for this kind of nucleation, what will happen, all as you are getting already a surface for the nucleation, so that time that energy requirement will be less, right? So that's why for heterogeneous nucleation, delta t term will be a very less, that undercooling you will need is less. But for homogeneous nucleation, that delta t is quite large. It sometimes it is greater than 200 Kelvin also, that delta T undercooling is you required. So it will depends kind of nucleations also. Is it clear? Okay. Mostly year wise. So first I'm covering the 2016. So actually, if you go to the Gate portal, you can see that total four slot is there for this session, right? So few of my colleagues are also there, few of my friends are also there. They are also solving this previous year question paper. So I mostly cover that physical metallurgy, that is a phase transformation part, that XRD or this kind of things, and the thermodynamics part. So I will mostly cover those part. Few of my friends are there; they will cover that extractive metallurgy things and all. So I will request to attend all these sessions, so that you can you can get the idea about all the questions, and you will all the question will be solved, right? So please attend these sessions and try make this as much as successful as possible. Okay. I also inform your friends also means about this session, so they can also join and they can also get in. Okay then. Okay, so we'll meet in the next Friday. It is on 26, right? Okay. Okay. Thank you all.